Wellhead power plants, an option to enhance the Macizo Volcánico del Ruiz geothermal project.
In 1968, CHEC began to investigate the geothermal potential of the Macizo Volcánico del Ruiz. In the 80s, the prospecting studies finding evidence of a heat source with the presence of fluids and geothermal potential. For this reason, CHEC processed and obtained the environmental license for exploratory drilling works in the 𝐏𝐻𝐻𝐻 Valley. In 1997, drilled the first geothermal well in South America in the 𝐏𝐻𝐻𝐻 Valley. The well reached a measured depth of 1,469 meters, with a temperature of almost 200 degrees Celsius at the bottom. In 2009, CHEC-EPM Group assembled a team to resume the geothermal project. The team's task was to examine existing studies, looking for new technologies that could add value to the project. From 2013 to 2016, CHEC and the company 𝐓𝐢𝐻𝐻 Group carried out geological, geophysical, geochemical, economic, financial, environmental and social feasibility studies of the project. Then, in 2016, CHEC and 𝐏𝐻𝐻𝐻 Company evaluated all the information that had been obtained to date on the project, to recalculate the volumetric model and define the drilling targets. The results of the new model show the feasibility of installing a 65 megawatts geothermal plant. CHEC is currently awaiting the completion of the environmental license update, to carry out deep exploratory drilling of 5 wells and studying ways to leverage the project. This project at the beginning of the exploratory drilling stage carries the highest levels of cost risk. According to the models that establish the phases of a geothermal project, when the drilling stage begins, the costs rise suddenly and the risk remains almost constant, due to the uncertainty about the existence of a viable geothermal reservoir for electricity generation. At this point, to continue with the geothermal project, it is necessary to overcome some barriers such as the high risks and investments in the exploratory drilling phase. The environmental authorities delays the study and authorization of permits for the development of projects. Infrastructure limitations and the need for specialized equipment and skilled workforce. The location of geothermal areas in volcanic zones without appropriate infrastructure, that can allow access and connection to the national electric grid. The lack of adequate legislation that allows the development and exploitation of geothermal resources and their efficient and effective participation in the energy market. The lack of knowledge in society and specifically in the political sectors about the benefits of geothermal energy development. The large supply of hydraulic-powered electricity at lower costs. In a traditional geothermal project with a central power plant, revenue is only generated after the field has been completed and the geothermal plant has been built. In some projects, wellhead plants have been used as a tool to deal with some of these barriers, since they have advantages such as wellhead units take 6 to 12 months to build, faster than a conventional central power plant. The anticipation of electricity production also generates anticipated revenue. The costs associated with drilling can be reduced as diesel is replaced on the rigs. Wellhead plants can facilitate workforce training in operation and maintenance aspects. Their costs make them more affordable, easy to install, and cheap to maintain and operate. Wellhead units can be portable and can be easily moved to other geothermal areas. With this technology, wells can be tapped almost immediately after testing. Their design and construction are standardized, making them more reliable. A great example of successful modular wellhead plants is the geothermal project in the 𝐏𝐤𝐢𝐳 Kenya field. Although production wells had already been drilled confirming the reservoir's viability for electricity production, 𝐾EN spent more than 8 years unsuccessfully trying to finance a central geothermal power plant. Noticing the challenges of the project, 𝐾EN decided to implement a 5 megawatts wellhead unit in one of its wells. The first wellhead plant was installed in 2011 and produced electricity for 18 months. At this point, 𝐾EN commissioned Green Energy Group to build 14 more wellhead units, considering the success they had with the first one. In 2016, all 15 plants, including the initial modular plant, came into operation, and together they have an installed capacity of 80.6 megawatts, producing electricity to this day. In addition to this, there are financial and technical studies that compare the use of wellhead units with central power plants or different combinations that link central and wellhead plants in the same field, with different installation times. These studies confirm the advantages offered by wellhead plants. The figure shows a comparison between a single flash central power plant, which had a construction time of 24 months, and a wellhead unit system per well, in which a wellhead unit was installed every 3 months, all in the same hypothetical geothermal field. In this case, the modular plant system not only produces more energy, because each well is optimized, but also has a higher net present value. Data from the 𝐏𝐤𝐳 study were used for sensitivity analysis, where it was shown that the construction time of the plant is a crucial parameter. Therefore, when the installation time of wellhead units is analyzed, it must be considered that they gradually come into operation in a staggered manner, unlike a central geothermal power plant that only comes into operation when all works have been completed.
To analyze the advantages of using wellhead plants in the Macizo Volcánico del Ruiz geothermal project, thermodynamic calculations were carried out in different electricity generation scenarios, using the estimates that already exist about the characteristics of the geothermal fluid. The figure shows the thermodynamic cycles that were used in the calculations. Single flash with back pressure turbine, single flash with condensing turbine, double flash with condensing turbine and binary power cycle for high enthalpy generation. These are the cycles that were considered adequate for the expected characteristics of the geothermal fluid. The estimates show that the geothermal reservoir in the Macizo Volcánico del Ruiz can support a single flash power plant with a 65 megawatts condensing turbine. The studies carried out in the area show that the geothermal fluid is found as a saturated liquid, at a temperature ranging between 240 and 260 degrees Celsius. In addition to this, it is estimated that each well can have a mass flow that is between 50 and 75 kilograms per second. Based on this, a hypothetical geothermal field of 12 producing wells was created, each well with its estimated productivity curve, which meets the conditions of the fluid expected to be found in the area. These 12 wells can power a 65 megawatts single flash central power plant.
Based on the curves and the resource estimates, various electricity generation scenarios with central power plants and wellhead units were evaluated. The thermodynamic calculations depend mainly on the type of cycle or on the type of system, central power plant or wellhead units. These systems and the power generated from the hypothetical geothermal field are shown in table. When the electricity generation technology is changed, a different net power is obtained from the same hypothetical field. For example, with the double-flash central power plant and the high-enthalpy binary central power plant, more energy is extracted from the fluid, compared to the single-flash central power plant. One of the advantages of wellhead unit systems is that the pressure in each well can be optimized to extract the greatest amount of energy from the fluid. It is for this reason that the system with 12 single-flash wellhead units with condensing turbine produces more electricity than the single-flash central power plant with condensing turbine, regardless of the fact that they start from the same operating principle. To establish the costs involved in a geothermal project, we take into account costs for pre-feasibility studies, cost for exploratory drilling, cost for planning and design, cost for production drilling, cost for generation plant, cost for substation and transmission, cost for operation and maintenance.
In each generation scenario, it is considered that there is a variation mainly in the costs of the plant, either by size or by type of technology. The variation by plant size was calculated with this equation, where CD is the plant construction cost, CC is the base cost that depends on the type of technology, and P is the plant power. The table shows the sum of all costs necessary to start up each type of generation system. This value includes the possible costs that may be incurred for the construction of each system, from exploratory drilling to transmission networks. For the financial projection, a plant life of 30 years with a capacity factor of 90% was considered. An electric power sale cost of $67 per megawatt-hour was estimated, based on conservative projections of the Colombian market and internal estimates of the company. In this work, a sensitivity analysis of the net present value was also carried out, with the variation of the construction time of the generation system. For central plants, this means that only until this construction time is completed, the plant is commissioned and the useful life begins to run. The figure shows the behavior of the net present value, with the variation of the generation system construction time. For the single-flash central power plant with condensing turbine, the double-flash central power plant with condensing turbine and the high-enthalpy binary central power plant.
The data shows how the increase in the construction time of the plant can severely affect the net present value of the project, to the point of making it unviable, lower than zero. It is also interesting to see how these delays in the completion of the plant eliminate advantages that exist in short construction times. For example, the binary power plant is the most attractive when the construction time is less than 3 years, but when the time increases, the double flash plant has a better net present value. In the case of wellhead plants, for example, when a construction time of 2 years is considered, it means that each of the 12 units had an individual construction time of 2 months. Therefore, after the producing well is ready, every 2 months a wellhead unit comes into operation. The figure shows the net present values for the generation scenarios where the field is developed with single-flash wellhead units with condensing turbine, binary high-enthalpy wellhead units and single-flash wellhead units with back-pressure turbine. The curve of construction time of the single-flash central power plant is shown to serve as a reference.
The data shows how the net present value of wellhead systems are less sensitive to construction time, because the startup is staggered. In contrast to this, the net present value of central plants is more sensitive to construction time, because any delay in the plant's entry into operation translates directly into a delay in the entry of the first project revenues. Finally, the figure shows the results for all generation scenarios. This analysis is relevant when choosing what type of electricity generation system to implement, since in countries with little experience in geothermal energy, the construction time may be uncertain. For example, in the Cerro Pabellón project in Chile, the central power plant was put into operation approximately 5 years after several delays, but the figure shows that 2 wellhead systems could have been a better option in this case, as they have a higher net present value with a construction time of 5 years.
Conclusions. The information presented shows how the construction time of the generation system becomes quite relevant when choosing the type of plant to be implemented in the project.
Contemplating the possibility of delays or uncertainties about the execution of the construction stages, it may be better to implement systems with wellhead units that are not as sensitive to increased construction time.
The data presented not only shows the economic advantages generated by the inclusion of wellhead power units in geothermal projects, but also the increase in electricity production by optimizing the pressure flow relationship of each well.
This work is currently under development, so further analysis is needed on the inclusion of modular wellhead plants in the Macizo Volcánico del Ruiz geothermal project.